We're going to be looking at some work I've been doing on GPS and Global Positioning System. And where you'll know about this is obviously your smartphone or your sat nav. And the way that that works is you're able to measure the distance between you and the satellites. And if you know how far 4 of these satellites are away from you, then you can work out your position on the globe. The way that GPS works is it has this signal that helps you with positioning, but it's also got some data that's encoded on top of it. It's sent very slowly, only 500 bits per second, so about 1,000 times as fast as the sort of slowest modems that people have grown up with. But it's enough to send data that tells you where each satellite is at each point in time. And that's essential because all you know is the distance. So if you want to know where you are, you need to know where they are. But it's got some other stuff in there. Some that we know about. So it talks about the satellite health to tell you whether to pay attention to it. It also tells you about what type of satellite it is. It tells you a bit about the atmosphere, so you can do some corrections for that. But there was one that stood out to me, which it just said, at the discretion of operating command. So it says text message, but it doesn't say anything else about what's in it. And this is not normally something that is going to be made available on your smartphone or even standard GPS chips. But if you have a software-defined receiver, then you can get it. So I had one of those from some other projects. I got a GPS antenna and then downloaded the right software to get the GPS data. And I saw these messages that, from a first glance, look random. And that is actually quite unusual. You don't really get random data in nature. Either someone makes it random or it's encrypted data. But either way, I thought it was interesting. And a lot of the work I've done on other projects, like the Tor project, are all about trying to make sense of encrypted data, and in particular, traffic analysis. So using the patterns in that encrypted data to work out what it means, what it tells you about the system. So how often it changes, how large is it, where it's coming from, all this sort of metadata can actually tell you more information than you can get from just the content. The GPS terminology is frames, and each frame is divided up into a subframe, and then some subframes are divided up into pages. So this particular data that we're interested in is present on one of these pages, and so it's sent relatively infrequently. It's only sent once every so often, but that's fine because you don't need it all the time. And what we found is that it changes once a day, sometimes less frequently than that. So I used the software-defined receiver to get started, and that gave me a handful of special messages that you could see from my house. But it's very hard to do anything with just a few messages when it comes to traffic analysis or cryptanalysis. You need a lot. So what I was able to do is get an archive of GPS messages that had been stored for, since 2007 from an archive in Potsdam, and then do the analysis on this. And we had a student at UCL who did a lot of work on trying to make that archive work. He then graduated, moved on to bigger and better things. So I took over and extracted the messages and then looked for some patterns in them. And then the first question I had was, well, like, what did they look at? That's always the best thing to do with data. And they look kind of random. It's not entirely random in the sense of random bytes, but the GPS specification says only certain characters are allowed. So from this set of characters that are allowed, they look pretty much random. That's just a feeling. If you want to actually understand whether something's random, you've got to do some statistics. And there's an interesting match between the information content of a message and its randomness and its ability to be compressed. So the more compressible something is, the less information is present in it. And that's actually one of the definitions of what it means to be information. And we measure that as entropy in bits. I used a technique called PPMD, which is where you take your corpus of messages, you leave one out, you compress it, and then you put that message then back in and see how much it grows. If it grows by a tiny amount, then that contains very little information, and that would happen if it could be guessed quite easily based on what you've seen before. But if it jumps by a large amount, then that tells you there's a lot of information in this message, and it's quite a surprising message. So I plotted each of the messages on a graph and had a histogram of this. And what it shows is that the messages are distributed almost entirely as you would expect if they were randomly selected, but not quite. There are some messages that are much more predictable than you'd expect, and a few messages are much more surprising than you would expect if these were just randomly generated. And so I looked at what these messages were. So the ones that were very surprising, term them sentinels, were things like all zeros, or all spaces, or in binary 101010, and that turned out to be a very important one. The ones that were much more predictable than you would expect were messages which contained some characters from messages that had previously been sent. So they weren't identical as before. If they were identical to before, I just eliminated those. I'm only looking at unique messages. But if they were almost the same but not quite, then in an information sense contains less information, but it's actually very surprising, because if data is random, you would never expect to see those. If data is encrypted perfectly, equally, you would never expect to see those. So it could be that those were mistakes, or it could be there was some emergency situation or something unexpected that caused the system to start outputting messages which were not the same as before, but almost the same as before. So that was the content that was surprising. The other thing you can do with these messages is that you can just count how often it changes or how often it changes per day. And roughly speaking, the entire constellation of satellites, so there's most of the time about 31 of them, are all sending the same message at the same time. And then they all switch over a fairly short period of time to a new message. But the period of time the constellation is sending a message has varied over time. That started off, when I had the data, about 3.7 days per message. Then something happened on this graph. You can see that something looked like it changed on the 26th of May 2011. But again, this is just a feeling, whether something changed or not. To make it robust, you need to do some statistical tests, and the technique I use is called cumulative sum, and that tells you when there's something different about the data from before and afterwards. And indeed, the pattern that looks like it's there is actually there, that round about the end of May in 2011, something happened. And after that period, the messages started rotating much more rapidly. So rather than being 3.7 days per message, it was about 1.8 days per message. That also raised the question of what happened then. And there's very little written about the features of GPS other than the ones that are used for positioning. But there was one presentation from someone working on the GPS system itself, and he was talking about the over-the-air distribution and over-the-air rekeying. So the system that most people use for GPS doesn't need any encryption keys or decryption keys. The signal's out there, the documents are published, you download the data, you can work out your position. The military have a different system. It uses the same satellites, but it uses encrypted data. And it uses that for two purposes. One is to stop spoofing. So because the GPS signals are public, you can predict not just where the signals would tell you are for your particular location. You can also predict what the signals would be for any other location in the world. And the signals are extraordinarily weak. They're probably the weakest signals you could imagine receiving. When it's transmitted, it's about the same power as a dim light bulb. And by the time it gets to Earth, it's almost negligible. And it's amazing you can capture it in the first place. But that means that if you have even a very small transmitter, you can easily overcome the satellite signal. So if you know what the signal would be in a different location, you broadcast that signal, then you're going to start confusing GPS receivers. That's exactly the sort of thing that the military were worried about happening in conflicts. So they made their encrypted system where not only do you need to know about your satellites, but you need to know this encryption key, and that encryption key is only distributed to the right people, so it'll be the US and their allies. And that makes spoofing much, much harder. It also makes it harder to jam the GPS signal, because if you don't know what the signal is going to be, then it's harder to come up with very precise jamming technology. So that works pretty well, but somehow you've got to get the keys out to the right people, but not to the wrong people. So you can't just put them out on the internet. You've got to physically go around all the GPS receivers, load the data on them, and then you've got to keep on doing this because devices will get lost, people might move into your alliance, they might leave your alliance, and so keys have got to have a relatively short lifespan and have got to be replaced regularly. So that problem is called initially key distribution, and then when you need to get new keys to people, that's called rekeying. And that used to be done entirely with glorified USB sticks that were plugged into these devices. But obviously that's quite labour intensive. So what this over-the-air distribution and rekeying scheme proposed is you could do it over the air, so over radio. However, the presentation did not talk about how the keys were distributed. And what was unknown was what mechanism was used. So was it the same satellites, different satellites, which frequency was used, because GPS uses multiple frequencies and so on. But the thing that really jumped out is that in 2011 is when it was advertised that the system started, and 2011 was also when we had this dramatic change of messages. Not just the change of the frequency that messages changed, but there was also one particular event in the content, and that was coming back to the Sentinel I mentioned, this 101010. So what happened is that there was one day, the 26th of May, where all the satellites stopped transmitting their random data, and they started transmitting just 10101010 and so on. At exactly midnight on the beginning of May the 27th, they then switched into sending, again, random data, but random data faster than before. So this was obviously a big event in GPS. It matches very closely what was mentioned as the over-the-air distribution and rekeying. And that's why I think that the text messages within GPS is likely the mechanism through which the rekeying and key distribution is done. I'm not certain, it could be other things. Journalists have asked the military what is the answer. They haven't got any response, unsurprisingly, but I think that's about as strong evidence as you can get from traffic analysis that that is what's going on.
And of course this, well, maybe not of course, but the Sentinel event that you've talked about, again, would have been completely invisible to people unless they were monitoring this specific frequency, not frequency, but part of the signal. Was that fair?
Yeah, so GPS receivers just ignore messages that they don't have any need to understand, and GPS receivers are designed for mainly positioning, also for getting precise time, and this is not relevant to either of those, so it just gets ignored. The higher end receivers have got debugging features where you can see this, but again, it's going to be ignored. Although we have seen some cases where GPS receivers have malfunctioned when unusual data appeared. And it wasn't in this case, as far as I know, but the 101010 pattern is interesting because it's actually not allowed by the specification. It's a violation. And there's been other cases where other fields in GPS have had this same sentinel pattern and the receivers have crashed. So there was an event where GPS receivers malfunctioned for something similar to this, but not the same as this. For the average receiver, this would have just passed without notice. The other thing I looked at is whether there was any announcement from the GPS operators that something was going on, and there wasn't. Like they make announcements every single day to talk about the state of the system, what's going to happen, what has happened. There's a lot of information in there, but at these periods and also other patterns I noticed, this is not discussed within their published documentation that they give out on the website.
So the suspicion is that it's probably something to do with that key, but of course we will never know.
Yeah, we certainly don't know. Maybe there'll be some leak, maybe they'll announce it. I don't think it actually needs to be secret. Like obviously, militaries, when they're talking about their classified system, naturally assume that everything is classified because there's not much harm in over-classifying in this context. There could be harm in releasing it, or at least it's going to require someone's careful thought about whether it's safe. So maybe this information will be published, maybe it's going to be leaked. But one reason that I felt free to talk about this is nothing I did was able to decrypt any of these messages. And even the case where I found unusual patterns that could be indicative of mistakes, those are long since in the past. And the keys that are used for GPS are valid for a week. So the keys have long since disappeared from relevance at the point that I published this.
And just one question on that subject of the keys. So this is encrypted data for encrypting keys that are for encrypting other data, is that right?
Yes.
So I'm wondering how they get the keys for this to get the keys.
So somehow the keys have to be loaded onto these devices initially. And in the old system, the keys had this 1 week lifespan, and so they'd have to be regularly replaced. In this case, the keys can have much longer lifespan because they're not keys for identifying the signal, they're keys for decrypting the key to identify the signal, or maybe some even further levels of indirection. So how this could work is that some keys go to the US military, a different key goes out to NATO, and then a different key goes to the allies that are working with them on that period. And then the broadcast that comes out using these special messages will be today's GPS key encrypted with all of those three keys. But then if they have a falling out with the people they're working with at the moment, then they don't distribute the key encrypted with 3 keys, they just distribute the key encrypted for 2 keys. And now those other people, even though they have a valid key, are no longer able to get access to the signal. So there's lots of complicated tricks that you can use to make this sort of key distribution work, but that's roughly the way that it could work. And there's some indications from this presentations that that's the sort of decisions that they're taking.
It is. But on that sphere, if Sean and I start walking due north and we keep our angles with the equator rigidly the same as each other, then the innate curvature of the Earth, so long as you are taking